Hello everyone, I welcome you all for the fifth session of the chapter Ray Optics. In our previous session, we had discussed about the refraction of light through the spherical surface and we obtained a very important relation which is relating the refractive indices of two medium and also the object distance, image distance and radius of curvature. So what is that expression? If you imagine a spherical surface, this is a spherical surface. Let N1 is the refractive index of the first medium and N2 is the refractive index of the second medium, and this is a principal axis drawn, and if this is an object which is emitting the light in two directions and this is the point where the two refracted rays are joined, and I have said that this is the position of the image and this is a position of the object, and this is the object distance which is a distance from the center of the spherical surface to the object, this is u, and this is the image distance v, and somewhere here we have a center of curvature c of the spherical surface, and this distance is called as a radius of curvature. So if we write a relation which is relating all these quantities, the relation looks like this: N2 divided by image distance v. N2 is the refractive index of the medium where the image is present. So N2 divided by image distance minus N1. N1 is the refractive index of the medium where the object is present, divided by the object distance u is equal to N2 minus N1 by the radius of curvature r. Okay. So this is the relation what we obtained from the refraction of light through a spherical surface. Now in this session what we are learning is what is a lens, what are the types of lens and sign conventions used for lens, and also a very important derivation which is a lens maker's formula. First let us understand what is a lens. A lens is an optical medium bounded by two refracting surfaces in which one of it or both are curved. If you consider the two refracting surfaces, this is one refracting surface and the other one is joined to this. Okay, so this is nothing but a lens. A lens is a refracting medium, or it is an optical medium bounded by two refracting surfaces in which one of which should be curved. Either this one or this one has to be curved or both may be curved. So this is nothing but a lens. Okay, so we have a lens like this also. What happens in this case? One surface is a plane surface which is also a refracting surface and the other surface is a curved one. Well, so this is also a lens and this is also a lens. So what is a lens then? A lens is an optical medium bounded by two surfaces, two refracting surfaces in which one of it or both are curved. Well, now let us look at the types of lens. Okay, let me write it here. Types of lens. So we have basically two types of lens. One is a convex lens and the second one is a concave lens. Okay, so we have two basic types of lens, convex lens and concave lens. First let me write what is a convex lens and how does it looks like. Convex lens, it is a type of lens, it is a type of lens in which edges are thin and center is thick. Okay, so this is a type of lens where the edges are thin and the center is thick. How does it looks like? We had already drawn the convex lens, so this is a convex lens. So you can observe it is bounded by two surfaces such that edges are thin and the center is thick. Okay, So here, why it is called convex? Convex means it is bulged outwards. The spherical surface is bulged outwards. So that is why this is called as a convex surface. So both the surfaces are convex as they are bulged outwards. This one is called as a biconvex lens. This is a biconvex lens, and this is called as a plano-convex lens. Okay, this is a plano-convex. Why this is called as a biconvex lens? Here we have two surfaces. The two surfaces are bulged outwards. That is why this is called as biconvex. Both the surfaces are convex in nature. That is why this is a biconvex. And this one, in this case, one surface is a plane surface and the other one is a convex surface. Other one is bulged outwards. So this is a plano-convex lens. This is a plano-convex lens. Then we have a concave lens. What do you mean by a concave lens? So this is just a reverse case of a convex lens. In concave lens, it is a type of lens in which the edges are thick and the center is thin. So if you observe, how does it looks like? Well, so this is a concave lens. You can see the edges are thicker and the center is thin. This is a biconcave lens. Biconcave lens. Why this is a biconcave lens? Cave means curved inwards. So the two surfaces are curved inwards. That is why this lens is a biconcave lens. And we have a plano-concave lens. Yes. So this is nothing but a plano-concave lens. This is a plano-concave lens because one surface is plane and the other surface is a concave surface. So this is a plano-concave. Well, so these are the types of lenses. Next. Now we need to define some of the important terminologies related to lens. For this, let me consider a biconvex lens. Let me name this as A and this as B, and let me draw a line which is joining the two edges A and B and this geometrical center. So after joining this line, if I point out the geometrical center, and this geometrical center of the lens is called optical center. Let me name this as some O. So this O is called optical center. Optical center. So what is this optical center? Optical center is the geometrical center of the lens. Then we had drawn a line which is joining the two edges and passing through this optical center, the line AB. This line AB is nothing but the effective diameter of the lens, correct? Because it is joining the edges and passing the center. So this line can be called as a diameter of a lens. So this effective diameter of a lens is called aperture. Okay, this is called as aperture. Fine. Next, let me draw an imaginary line which is passing the optical center and perpendicular to the aperture. Correct? Let us name this as some x dash x, and this x dash x is called a principal axis. Principal axis. So what is principal axis? A principal axis is an imaginary line passing through the optical center perpendicular to the aperture. So this is called as a principal axis. Next, so let us say that a parallel beam of light is incident on the convex lens. Let us say that an object is placed at somewhere infinity, a parallel beam of light. You can see a parallel beam of light is incident on this convex lens. See, when the parallel beam of light is incident on a convex lens, the refraction takes place on this convex lens at this aperture, and all these rays are going to bend towards the principal axis. So, if you draw a refracted rays like this, all the refracted rays are joining at the one common point, and let me name this as F. So when the parallel beam of light is incident on a convex lens, the refraction takes place at this aperture, and all these refracted rays are joining at the common point F, and this point F is called principal focus. Principal focus. Well, what is principal focus? It is a point on the principal axis such that the refracted rays converges to that point in case of a convex lens. Okay, this is called as principal focus. So principal focus is a point on the principal axis such that the rays after refraction, that is refracted rays, converges at that point in case of a convex lens. So this is called as principal focus. Next term, the next term is very important again, a distance between this optical center to the focus. Okay, the distance between optical center to the focus, which is termed as F, and this small f is called focal length. Okay, this is called as a focal length of a lens. What is the focal length of a lens? A focal length of a lens is the distance between the optical center to the principal focus. The distance between optical center to the principal focus, we call that distance as focal length. So what are the terms we had defined here? First term is an optical center. Optical center is the geometrical center of the lens. Then we define what is an aperture. Aperture is a line, or it is a effective diameter of the lens. Then we define what is a principal axis. A principal axis is an imaginary line which is passing through the optical center and perpendicular to the aperture. Then when a parallel beam of light from an object which is at infinity is incident on a convex lens, the refraction takes place at the aperture and all the rays are going to converge at a point F, and this point F is called as a principal focus. And we define what is this principal focus. What is principal focus? Principal focus is a point on the principal axis such that the refracted rays converges at that point in case of a convex lens. Then we define what is a focal length. A focal length is the distance between the optical center to the principal focus. See, I said that when a parallel beam of light is incident on a convex lens, the rays are going to converge at F. But this will not happen in the case of a concave lens. What may happen here? If you observe, let us say that we have a concave lens, and for this concave lens, let me draw an aperture and also mark the optical center O, and this is a principal axis. Okay. Now, let a parallel beam of light is incident at the aperture of the concave lens. Let the parallel beam of light is incident at the aperture of the concave lens. Now what happens is the rays are going to diverge. Okay, the rays are going to diverge. They are not converges, or they are not bending towards the principal axis. They are just diverged. Okay, but if I trace back these refracted rays in the backward direction, it appears that all the refracted rays are appearing to coming from a single point. Yes. So if you observe this point, all the refracted rays, all these refracted rays are just appearing to diverging from this point, correct? It is not actually diverging from that point, but all these refracted rays, if you trace back their directions, and you get a point F, where from that point the rays are appearing to diverge. From this point the rays are appearing to diverge. So this point F is now called as a principal focus of a concave lens. Okay, so here we define a principal focus as it is the point on the principal axis such that the refracted rays converges at that point for the case of convex lens. But in case of concave lens, a principal focus is a point on the principal axis such that the refracted rays are appearing to diverge. They are not actually diverging from that point, but they are appearing to diverge from that point. So this is a principal focus of a concave lens. Okay. For this reason, convex lens is called a converging lens because it converges the incident beam of light. So convex lens is called as a converging lens. It is a converging lens. And this lens, a concave lens, diverges the incident beam of light. So this lens is called as a diverging lens. So this is a diverging lens. Okay. So this is the basic difference between the convex lens and concave lens. When a parallel beam of light is incident on a convex lens, it converges to a single point, and in case of a concave lens, when the parallel beam of light is incident, it will diverge the rays. So that is why this lens is a diverging lens, this lens is a converging lens. Okay. Now let us move on to the next one, which is sign conventions for the lenses. Let us write that. So for the lens, we follow a Cartesian sign conventions. So let me consider a convex lens with principal axis, optical center and an aperture. Okay. Imagine we have placed a linear object somewhere here. This is a linear object of height HO, and let us say that this is the direction of the incident light. You should understand that an object is always kept to the left of the lens, and the direction of incident light is always from object towards the lens. So this is the direction of incident light. And imagine somewhere here the image is formed, which is an inverted image. We can call that as a real image. We will study this about later. Let me say the distance from this optical center to the object. So this is considered as u, object distance u, and this distance, a distance from the optical center to the image. So this is an image of height hi, and let me say this is a distance v. Now how do we take the sign conventions while measuring these lengths? If you imagine a Cartesian coordinate system with this is positive x-axis and this is negative x-axis, this is positive y-axis and this is negative y-axis, and the intersection of the coordinates is called as an origin. So from the origin towards the right side, the distances are considered as positive, and towards the left side, the distances are considered as negative. In the same way, from the origin, the distances above are positive and below are negative. The same way we follow the conventions in lens also. So for this one, the first sign convention says all the distances are measured from the optical center. The first sign convention is all the distances are measured from the optical center of the lens. So I said that this is the optical center, and from this point we have to measure all the distances. Well, the second one is the distances measured along the direction of incident light, are taken as positive, and the distances opposite to the direction of incident light taken as negative. Okay. The second point says the distances measured along the direction of incident ray are taken as positive and the distances measured opposite to the direction of incident light are taken as negative. Say for example, we have an optical center here. From optical center to the image, the distance is called as image distance. So this image distance is taken as positive as the distance from here to here is along the direction of incident light, or it is towards the right side of the optical center. So this distance is considered as positive. Now from optical center to the object, the distance, this distance is object distance, correct? An object distance is measured from optical center to the object, which is opposite to the direction of incident light, or it is towards the left side of the optical center. So this distance is considered as negative. So the second point says the distances measured towards the direction of incident light are taken as positive and opposite to the direction of incident light are negative, which follows the same sign convention as the Cartesian coordinates. Okay. The third point says, so what does the third point says? The distances measured above the principal axis perpendicular to it are taken as positive and those distances measured below the principal axis perpendicular to it are taken as negative. For example, this is the object which is kept above the principal axis, correct? So this distance, I said that HO is the height of the object. So this distance is measured above the principal axis and perpendicular to it. So this distance is considered as positive, and this one, the height of the image which is below the principal axis, that is why this height is considered as negative. Okay. So this is the third point. So these are the sign conventions for the lens we have to follow. Now we need to derive a very important relation which is called as a lens maker's formula. This derivation is very important from your examination point of view because this question has repeated several times in your exam. So let's derive this lens maker's formula. First, let me consider a biconvex lens. We have a biconvex lens. This biconvex lens is bounded by two refracting spherical surfaces, correct? So let me say ABC is the first spherical surface, a spherical refracting surface, and ADC is the second spherical refracting surface. So this lens is bounded by two spherical surfaces ABC and ADC. So let us mark the geometrical center, which is nothing but a optical center, and let me name that as some O dash, and let us draw a principal axis. This is an aperture. When the object is placed somewhere here, this is an object O, then the distance from this optical center to the object can be taken as object distance. So let us say that this is an object distance U. This is an object distance U. Okay. Now, the rays are emitting from this object and which is incident at the aperture of the lens, and it forms an image, a final image somewhere here. Okay. This I is the final image. Therefore, this distance is taken as some V. So for this surface ABC, here we have a center of curvature C1. Therefore, the distance from optical center to the center of curvature is R1, which is the radius of curvature for the first spherical surface. And somewhere here we have a center of curvature for the second spherical surface ADC. Therefore, this distance is taken as R2. Okay. R2 is the radius of curvature for the second spherical surface. Now, I said that a lens is bounded by two refracting spherical surfaces, that is ABC and ADC. So while deriving this, we need to consider the refraction is taking place at both these spherical surfaces. Okay. So you should remember a formula which has derived in the previous class, that is a refraction through a spherical surface, correct? So here we imagine that this final image I is formed because of the refraction through the two surfaces ABC and ADC. So we have to consider that separate now. So for the first surface, let me write, for the refraction at the surface ABC, okay, for the refraction at the surface ABC, this object O acts as object, therefore O is an object at a distance of U, okay, and this object is in a first medium. Say this is a first medium of refractive index N1. Inside the lens, the refractive index is N2 and again this is N1. Now for this surface ABC, let me draw the surface ABC. Let me draw the surface ABC. So this is a surface ABC, and for this refraction from the object, the light is incident at the surface ABC, that is for this, and an image is going to form somewhere at I dash. This I dash is not a final image. This I dash is not a final image. It is the image formed because of the surface ABC, okay, at a distance of V dash, okay, at a distance of V dash. So this I dash, the image I dash is formed in the second medium of refractive index N2. So here we need to consider the two refracting surfaces. N1 is the refracting surface, N1 is the refractive index of the medium where this object O is present, and N2 is the refractive index where the image I dash, which is not a final image, and this is formed here at a distance of V dash, okay. Therefore V dash is the image distance and this I dash is the image for the spherical surface ABC. Now I know the object distance is equal to U, object distance is equal to U, and what about the image distance here? The image distance will be V dash, okay. So the image distance is V dash for the spherical surface. Now remember the formula which we have written in the starting of this session. So what is that formula? Refractive index of the medium where the image is present divided by the image distance, correct? Refractive index of the medium where the image is present and that divided by image distance V dash minus N1, that is the refractive index of the medium where the object is present, that is N1 divided by the object distance. So this object distance is already considered as U in this case. So this will be U and this is equal to N2 minus N1 whole divided by R1, where R1 is the radius of curvature for the surface ABC. So we got an expression 1 which is obtained by considering the refraction is taking place from the first surface ABC. So this is the refraction due to the first surface ABC. Now we will consider the second refraction, the refraction due to the surface ADC to form the final image. So this surface ABC is refracted the light and is already formed an image at, which is formed an image I dash in the second medium, correct? And now we should consider the refraction through this surface ADC. Let me write it here. For the refraction at the surface ADC. So for the refraction at the surface ADC. So for this refraction, it is very important to note that this I dash, an image which is formed because of the surface ABC, acts as a virtual object. Okay, so this I dash, which is an image formed because of the first surface ABC, and this I dash acts as a virtual object. So this I dash acts as a virtual object which is in a medium of refractive index N2. So that's a very important point to remember. So let me write. So for the refraction at the surface ADC, I dash is a virtual object at a distance V dash. So in this case, the object distance is taken as the object distance is taken as object distance is equal to V dash. Okay. So for the second refraction, that is the refraction through this surface ADC, I dash acts as a virtual object and this distance becomes a object distance V dash. Now let me write the diagram for this. So this is a surface ADC, this is a surface ADC, and this is a principal axis, and this I dash is an object now. So what is the medium of this object, which is in the medium of refractive index N2, and now it has to form the final image. So the light is incident from this object, from this virtual object at the surface ADC, and it forms an image and it forms an image somewhere here. So as you can see here, this I dash is a virtual object, and finally when the refraction takes place at the surface ADC, it forms a final image I at a distance of V here. Okay, so let us write that. So this I dash is the object distance, which is already marked as V dash, and this I is the position of the final image formed because of the refraction through both the surfaces. So this will be distance V. Okay. Now let us use the same expression to write that one. The object is in a second medium of refractive index N2 and the image is in a first medium because the final image is formed in the first medium. The refractive index of the medium where the image is present is N1. Okay, that's a very important point to remember. So now let us write this equation for that one. Refractive index of the medium where the image is present, that is N1, divided by the image distance V minus refractive index of the medium where the object is present, that is N2, divided by object distance is V dash, object distance is V dash, is equal to, see here the refraction is taking place from first medium to second medium, correct? From first medium to second medium. In this case, the refraction is taking place from second medium to first medium. Therefore, right hand side of the equation becomes N1 minus N2 here. Okay, so that has to be remembered correctly. So this will be N1 minus N2 whole divided by R2. So what is that R2 is? R2 is the radius of curvature for the spherical surface ADC. So this R2 is the radius of curvature for the spherical surface ADC. Now let me say this is equation 2. We got an equations 1 and 2 now. So we have to add the two equations in order to get the final relation. Okay, let us add them. So we have equations 1 and 2. Let us add them. Adding equation 1 and 2. Let us add the left hand side of the equations first. This is N2 by V dash minus N1 by U plus N1 by V minus N2 by V dash. So this is equal to, let us add the right hand side now. This is N2 minus N1 by R1 plus N1 minus N2 by R2. So now we are adding the left hand side and right hand sides of the equations 1 and 2. Let us proceed further. So what happens here? So you can cancel this N2 by V dash minus N2 by V dash on the left hand side, and what remains now is N1 by V minus N1 by U is equal to, here N2 minus N1 by R1, N2 minus N1 divided by R1 plus N1 minus N2 divided by R2. Okay. Here N1 is common, the term N1 is common here, so let me take that out. N1 into 1 by V minus 1 by U, that is equal to, let N2 minus N1 by R1 is kept as it is, plus, so in this term I will take out this negative sign outside, so the sign will change here. N1 minus N2 becomes N2 minus N1 if I take the negative sign outside. So if I take this minus outside, what remains is N2 minus N1, correct? So even though if you multiply this again, you will get the same expression. So nothing will change. Now if I multiply this minus with this plus, plus into minus becomes minus. So therefore in the middle we get minus, okay? Divided by R2, divided by R2. So we get N2 minus N1 by R2 now. So see, Now see, you can take these two terms common outside. Therefore, n1 into 1 by v minus 1 by u is equal to n2 minus n1 is taken outside, and what remains is 1 by r1 minus 1 by r2. Okay. Now in the next step, take this n1 to the denominator of this equation. So what you will get is 1 by v minus 1 by u is equal to, this n1 is divided here, so this is n2 by n1 minus n1 by n1 into 1 by r1 minus 1 by r2. Now say that for a convex lens, if the object is at infinity, the image is formed at the focus. Okay, I already explained you that when a parallel beam of light means the object is at infinity. Object is at infinity means object distance is equal to infinity. Therefore, for an object to be at infinity, the image is formed at the focus, correct? The image is formed at the focus. So, this is f. Therefore, the image distance becomes equal to the focal length. The image distance becomes focal length. In which case this happens? When the object is at infinity, that is object distance is infinity, image distance is equal to the focal length. By applying this condition here, when the object is at infinity, that is u is equal to infinity, v is equal to f. So by applying this here, we get 1 by, instead of v, I will write it as f, minus 1 by u is taken as infinity, that is equal to n2 by n1 is written as it is, n2 by n1 minus n1 by n1 is 1. So this into 1 by r1 minus 1 by r2. Finally, 1 by infinity is 0. What we will get is 1 by f is equal to n2 by n1, refractive index of medium 2 divided by refractive index of medium 1. This can be written as n21, which is a refractive index of medium 2 with respect to medium 1. So this is n21 minus 1 into 1 by r1 minus 1 by r2. So this is the required expression. It is called as a lens maker's formula. 1 by f, f is a focal length. So 1 by f is equal to n21 minus 1 into 1 by r1 minus 1 by r2. So f is a focal length, n21 is the refractive index of medium 2 with respect to medium 1, r1 is the radius of curvature of the first surface, r2 is the radius of curvature for the second surface. So this derivation or this expression is called as a lens maker's formula. So which will be asked for 5 marks in your exam. So which is a very important one, and you should understand the derivation very clearly. Well, in this class, what are the things we have studied? What is a lens? What are the types of lens? And the important terminologies related to lens and sign conventions, and also we derived a lens maker's formula. In our next session, we will be studying about the refraction at a prism. Until then, thank you.